Chapter 5, Section 4, Data Reduction. As the final section of Chapter 5, let me talk about data reduction. Data reduction is necessary to reduce the computation time and make data handling more efficient. A large size of dataset seems to contain much information. In a case of data frame, a data frame with many rows and columns seems containing much information. In other words, large-sized data seem to have much information. However, there are some difficulties in managing a large-sized dataset. First, it requires a large capacity for data storage. Second, it requires much computational time. Third, data preprocessing and modeling becomes more time-consuming. Moreover, a dataset with too many columns are likely to fall into a problem called overfitting that will be covered in the following lectures. So, we sometimes need to reduce data by delete unnecessary rows and unnecessary columns, as we have already seen in the section of data cleaning. In this section, we focus on the operation for reducing the number of columns. The operation is called dimensionality reduction. As you know, a data frame consists of rows and columns. In data science use of term, the dimension refers to the number of features in a dataset. In a data frame, the dimension is the number of independent columns. A data frame with a large number of dimensions seems to contain much information, but it is not always the case. In some cases, two or more columns store similar information, and thus having those columns provide us with little informational benefit, just increasing the computational cost. Moreover, a data frame with too many dimensions is subject to a problem called the curse of dimensionality. So, sometimes it is useful to reduce the number of dimensions of the data by deleting unnecessary columns and integrating some columns. However, it is important to know that we should do it while keeping meaningful information as much as possible. These operations are called dimensionality reduction. More formally, dimensionality reduction can be defined as the data transformation to reduce the number of features in a dataset, while retaining as much information as possible. To understand the necessity of dimensionality reduction, we first need to understand a problem called curse of dimensionality. Curse of dimensionality is a problem that increase in data dimensions results in exponential increase in the amount of data we need to develop a generalizable model. Suppose we try to build a model that predicts an employee's job satisfaction level. Suppose we have data of 100 employees. We have a feature of gender. And suppose our employees consist of 50 male and 50 female. In this case, we can predict job satisfaction using gender as a predictor based on 50 observations. It is not a large sample, but we can expect a certain level of generalizability. Now, we have another feature, job type. Suppose job consists of two categories, administration and sales. By combining gender and job type, we have four categories. And if the job type is almost evenly distributed, each category consists of 25 people. Now, we have an additional feature, age group. Suppose age group consists of 5 categories, 20s, 30s, 40s, 50s, and 60 and above. By combining these three features, we have 20 categories. If age group is almost evenly distributed, each category consists of 5 people. So, if we predict job satisfaction using these three dimensions, we make prediction by observing only 5 people. So, it is possible that our prediction is specific to these 5 people. So, not generalizable. If we need at least 50 samples for each category to make a generalizable prediction, we need to have 100 observations when we have only one dimension, gender. But if we have two dimensions, gender and job type, we need to have 200 observations. And if we have three dimensions, gender, job type, and age group, we need to have 1,000 observations. We can see that the amount of data to build a generalizable model is exponentially increasing. Increasing data is not always feasible, so it is useful to utilize dimensionality reduction technique to deal with this problem. There are two methods for dimensionality reduction: feature selection and feature extraction. Feature selection is to select only important features from a dataset. We have already seen some criteria and methods for deleting unnecessary columns. There are kinds of feature selection. Feature extraction is to create new features by combining multiple features. In both methods, what is important is to do it while retaining as much information as possible. Feature selection and feature extraction are performed in the process of data preprocessing. However, we sometimes implement them in the process of modeling. This section focuses on feature selection and feature extraction in data preprocessing phase. A basic principle for performing dimensionality reduction is that we need to reduce dimensions while retaining as much information as possible. In other words, we should reduce dimensions while minimizing information loss. Dimensionality reduction is associated with information loss from the dataset, so we should minimize the amount of loss. So, when we delete features, we need to consider how much information each feature contains. An important criteria of how much information contained in a feature is the variance of the feature. Let's consider it using an example. For simplicity, let's consider an extreme case. Suppose we have data of 5 employees' job satisfaction level, skill level, and individual job performance. And suppose we want to predict individual performance using job satisfaction and skill as predictors. Here, all employees are the same level in job satisfaction. So, even though we have 5 observations, the plot shows only one dot because all the observations are overlapped. On the other hand, their skill levels are widely dispersed. That is, the variance is larger for skill level than job satisfaction. Let's create plots that show the relationship between these predictors and performance. The upper right plot represents the relationship between job satisfaction and performance. The performance level is widely dispersed, but job satisfaction levels are the same for all employees. In other words, the level of job satisfaction is the same irrespective of their performance level. So, job satisfaction is useless for predicting performance level. Let's see the lower right plot, which represents skill-performance relationship. Since both skill and performance are widely dispersed, it is possible that we can find clear relationship between them. This case is a simplified one. We cannot always see such clear relationship. But we can say that if the variance of a feature is very small, the feature is useless as a predictor because the values of the feature are the almost same, irrespective of the level of outcome variable. That is, A feature with little variance has little information for explanation and prediction. On the other hand, a feature with large variance can have much information for explanation and prediction. As we have seen in the section of data transformation, we can create a new variable from existing multiple variables. This operation can be regarded as a part of feature extraction if it results in reducing dimensions. Principal component analysis is an advanced technique of feature extraction. It is called PCA for short. Details of PCA is beyond of this section, but we can say that PCA is a statistical method to summarize correlated features by a smaller number of principal components and thus reduce the data dimension. PCA reduces the data dimension while retaining as much information as possible. Here, variance represents the amount of information. To do it, PCA converts features by orthogonal transformation. It is a statistical process that converts the observations of correlated features into a set of linearly uncorrelated features with the help of orthogonal transformation. Let's see a simplified example. Suppose we have these three data points. They have two features, x and y. So, these data points can be expressed by a horizontal axis, x, and a vertical axis, y. The data has two dimensions. However, if we convert the axis represented as k, we can express the same information by only one axis. The new axis is the principal component that summarizes data by fewer dimensions. And as we can see, the variance of a principal component is larger than those of x and y. So, the principal component retains the information of original data. It is not always the case that raw data we obtain is ready for analysis. So, we need to pre-process our raw data to make it ready for the following analysis. Data preprocessing is sometimes the most time-consuming in a data analytics project. We perform data preprocessing to make the following analysis more efficient and effective. Data preprocessing consists of data cleaning, data transformation, and data reduction. They contain operations that delete or compress some parts of the dataset. However, as a fundamental principle, we need to do it while retaining as much information as possible. Data preprocessing is an iterative process. We sometimes need to preprocess the dataset again after completing the phases of data preparations and exploration. Thank you for watching. Please thumbs up and subscribe to my channel.